So welcome to linear algebra. So far we have discussed 3 lessons and now we are going to move on to the next lesson, which is chapter 4, that is regression and model selection. So we are going to start with regression and model selection. Now I want to kind of emphasize this because with this chapter, we are officially going to enter the machine learning and deep learning type of stuff. So initially, when people started working in this area, like deep learning, machine learning, so the start was with regression. It was with the regular regression, robust regression, multivariable regression, and then gradually it evolved into neural networks, then multi-layer neural networks, deep learning, and all that type of stuff. So again, some of the material that we are going to talk about, we have seen this already. For an example, we start with an equation ax is equal to b. Now, if a is given, b is given, and the dimensions match, then probably we can use some type of technique for simultaneous equations, some type of matrix algebra to find out the value of x. Now, the problem comes when the model is not prescribed, which means A is not well defined, not completely known, or basically B has some zeros, or if the number of equations are less or more than number of unknowns. So in that particular case, you have something called as underdetermined or overdetermined system. So you can have an underdetermined or overdetermined system. And to solve these types of problems, what we need to do is we have to use optimization technique. So optimization. And optimization is a huge field that is used in control theory, machine learning, dynamics, data-driven modeling, and so on. So typically, the optimization problem, what we studied when we looked at the first calculus course, is something like take the first derivative and equate it to 0. But in terms of adding a constraint, we define the constraint as something like argmin. This is the minimum value. We are trying to perform a minimization, wherein we are trying to minimize the absolute value of the difference between ax minus b plus some value lambda times g of x. Now, wherein, again, please understand, this is called as penalization. So this is the given penalization. So I want to tell you what that means. So, and lambda is the scalar or the penalty parameter. So lambda is like the penalty parameter. Now, this needs a little discussion. So what are we trying to do here? The idea is we somehow want to satisfy Ax is equal to B. But unfortunately, Ax is not going to be equal to B. So here is the problem. If we find out the value of x's, so we find these values so that when we substitute these values, left hand side is equal to right hand side, then the equation is solved. But unfortunately, because of the properties of the system or the properties of the model, Ax, no matter what we do, is not equal to B. So what that means is we are going to have an error, and that error is going to be Ax minus B. This error could be positive or negative. So our objective is to minimize this error. So what we want to do is we want to find out the absolute value of error, and I want to minimize that error. But this minimization can be performed in multiple ways. For example, what does minimum mean? Minimum means the distance minimum. Minimum means the minimum square of the distance, or minimum means out of this 10 different values, the least or the lowest possible value. So we don't know what minimum is, because minimum for me may not be minimum for you. So we define this minimum in terms of L2 norm, which what it means is we look at to minimize the square of the square root of the distances. So basically it is nothing but E1 square plus E2 square, etc., and then try to do the square root. So this is the type of minimization that we want to do. Now here comes another problem, that this minimization we may or may not be able to achieve. So what that means is we can't achieve the perfect minimization. So we want to penalize or somehow modify this minimization. And that modification is achieved by this lambda g of x. And we are going to do an argmin, which is the minimum value. So this is what is the meaning of that expression. The other value or other way to define this is something like argmin, the minimum value of g of x subject to the absolute value of ax minus b2, which is less than epsilon. And you will see that in literature, this technique is used multiple ways. Sometimes they call this as the variational formulation, which is an approximate ways to solve the problem. But at the end, this is what it is. Like, we want to minimize a quantity. If perfect minimization is not achieved, we are okay with some approximate minimization that will give us reasonably accurate results. Now, again, we have this choice on penalty. So basically, we can decide what type of function that we want to use. So basically, this is the penalty, and we have choice on this penalty. And this penalty function or the constraint function is called as regularization. And you will notice this regularization word quite often used in the optimal control problems. So for an example, you can assume this g of x. So something like minimum of g of x is nothing but minimum norm of x2. What that means is minimum of x1 square plus x2 square plus x3 square, etc. So you can you can use some function that achieves this regularization. Now, this problem is really tricky when we look at nonlinear models. So here we can think about this is sort of a linear model. So this is the linear model. But if you have a nonlinear model, so if we have a nonlinear model, then solving this equation in a closed form may not be possible, and we have to resort to numerical techniques. And in that case, we use this algorithm called as gradient descent. And this gradient descent algorithm is very commonly used in machine learning or neural network and network tuning. So the idea is something like this. So what is the purpose of optimization? So purpose of optimization is, or minimization is, find out the minimum value. So if I have this value of x and this is f of x, what I want to do is I want to find out the minimum value. Now recognize that the function is sort of minimum here and function is minimum here. This is the global minimum. So all across the domain. So from, say, for example, x is equal to 0 to say x is equal to 10, the function f of x is the least at this point. And let me say this point is at 5. And this is local minimum, which means the function is minimum, but this is not the absolute minimum. So if this function is nonlinear, how do we approach this problem? So gradient is nothing but derivative, so or nothing but the slope. So what I'm going to do is I'm going to find out the slope over here. Clearly, slope or the gradient is increasing. So basically delta x is increasing, which means if I were to go towards right, clearly the function value is increasing. Now, if I were to go in this direction, as you can see that my gradient is decreasing. As I go to this point where my gradient is the minimum, and then when I go over here, so I want you to kind of think about this cusp. So you would notice the gradient on one side and gradient on the other side is different. So here the gradient slope is decreasing, here the slope is increasing. So what that means, if slope is increasing and decreasing, this is the point where the slope is 0. So this could possibly be a minima. But again, this is a numerical technique. So we are going to do this numerically. So we don't know if this is the local minimum or global minimum. And that is one disadvantage of gradient descent. So for gradient descent, it's good in finding local minimum. But if you want to find out the global minimum, you need to start at different points. So for an example, you have to start over here, you have to start over here. And if wherever you start, depending upon where you start and depending upon what direction you proceed, you will be able to find out a local or the global minimum. And now the question comes is, this is just a function. So there is only x and function is f of x. Imagine if you have a case wherein the function is dependent on 2 or more variables. So if the function is dependent on 2 or more variables. So imagine that you have a surface which is something like this. And this surface has these different surface lines. So how do we proceed? So in this case, what we need to do is we need to proceed again in 2 dimensions. So basically, what needs to happen is you need to go towards one axis and then you need to go towards the other axis, and kind of you have to follow this zigzag type of path to finally get down to the local minimum. And you want to be careful about overfitting and underfitting. So what is the meaning of overfitting? Overfitting is something like this. Imagine that you have the data set and you want to fit a line. So you want to actually try to fit this through all these points. That is the overfitting. And underfitting means basically you are fitting through only few points. And both of them are not good. Because if you decide to overfit, the number of iterations that you want to perform, or they are also called as epochs, E-P-O-C-H, which is the iterations, they increase. And then basically, if you increase the model complexity, you may or may not be able to get a meaningful solution. But if you underfit, so this is the overfit, and if you underfit, your model may not describe the nature of the data. So with underfitting and overfitting, you need to be very careful. And what happens is, one thing that it's commonly discussed is the effect of error. So for an example, if you have the model complexity, so you have model complexity on x-axis, and if you have error on y-axis, so with overfitting, you would observe that if you want to fit the data onto the limited data set and then test the data on the data set, you would notice that your thresholds for training and validation, they are like this. So this is training and this is the threshold. Now this needs a little discussion. For example, if you have a function, so if you have a function that is dependent on x and y, so z is equal to x and y, and now z is expressed as some numbers. So basically you have the values of z, you have values of x, and you have values of y. And what you want to do is you want to come up with some type of a fit. To make sure that the fit is okay or not, what I would do is, and here is all this data. Here is all this data. What I'm going to do is, I'm going to select subsection of this data, create the fit, and then I'm going to test it. So this is like training. So I'm going to find out my curve fit or my regression on this training data set. And then I'm going to test this equation on the withheld data set. So this will be like testing. So if I were to have an overfitting problem, the withheld data error will continuously increase. On the other hand, this is for overfit. On the other hand, for the underfitting, you have this model complexity. And this error. And if I were to do underfitting, so this will go like this. Now, objective function, what we are trying to optimize, are we optimizing with respect to cost? Are we optimizing with respect to time? Or what is our aim? So objective function and also the regularization. Those are two important parameters or important decisions that the engineers have to make before we try to solve the problem. Now, in the past, we have spent a lot of time on looking at the curve fitting, but I want to actually talk about curve fitting in terms of different norms. So norm, you will see this word norm is sort of a metric or a criteria. So norm means it's also sometimes called as metric or criteria. So for an example, if you have a vector, say 1, 2, 3, and you have second vector 4, 5, 6. Now the question is, how do I compare this vector A or x1 with vector x2? So if it was numbers, like if it's just 1 and 4, 2 and 5, 3 and 6, that's very easy. But imagine if I have something like maybe 1, 12 and 3 and 4, 5 and 6. So which vector is greater? So for that, I need to come up with some type of a matrix. So that's what is called as norm. So for an example, I can choose one type of norm would be, I would find out the square of this number, square of this number, square of this number, and find the value. Then I would take 4 square plus 5 square plus 6 square and find these values and say this A and I find this B. And if I say B is greater than A, then I would say vector x2 is greater than vector x1. Some of you may say, hey, that is not the metric that we want to use. And maybe what I would do is I would just choose the summation. So 1 plus 12 plus 13. So I would use 1 plus 12 plus 3. And I would choose 4 plus 5 plus 6. And then I would use this as a means for comparison. So similarly, norm is one way or a technique for comparison. So there are quite a few norms that are popular. One of the norms is maximum error norm. Maximum error norm. And this maximum error norm is defined as E infinity of function f, which is equal to maximum, and basically you run this increment from value 1 all the way to the value of n. And I would do something like absolute value of f of xk minus yk. So let's try to identify this maximum error norm. So I'm gonna do maximum error norm is 1 minus 4, 12 minus 5, 3 minus 6, and then this value is going to be minus 3. This value is going to be 12 minus 5, 7, and this is going to be minus 3. I'm going to do the absolute value 3, 7, 3, and maximum error, this norm is 7. So this is the maximum error norm. The second norm for comparison is mean absolute error. Mean absolute error. E1F is equal to 1n summation k is equal to 1 to n absolute value f of xk minus y of k. So what that means is, if I were to do the mean absolute error, this will be 3 plus 7 plus 3 divided by, I have 1, 2, and 3. So n value is 3. So 3 plus 3, 6. 6 plus 7, 13. So 13 by 3 is the mean absolute error. And the last norm that is typically used is the least square of error. Least square. And this least square error is called as E2 norm, which is 1 divided by n summation k is equal to 1 to n f of xk minus yk square root. So if I were to perform this, this is going to be something like 3 square minus 3 square plus 7 square plus minus 3 square. So 18 plus 49 divided by 3, and I would do the square root. So this is the least square error. So these are the 3 different norms. And what I want to do is, I gave a simple example. Now I'm gonna change my screen and I'm gonna share my screen, and I will show you the MATLAB script. I will show you the MATLAB script. So what I want to do is, I want to look at the linear regression. So in this linear regression, I have the values of x, I have the value of y, and what I want to do is, I want to find out the fit based on different types of norms. And please understand, E2 is a very simple norm that we use all the time, but E1 and E infinity is also used. So for an example, if you are into control theory, there is something called as optimal control. For optimal control, we use E2 type of norm. There is also called as H infinity control, wherein we use the maximum error norm. So if you decide to pursue career in control theory, then you will notice that that is something that can be used. So now I'm going to run this code, and I want you to, if you have the files, please run those. And now you will see the fits. So this is the same data set. So we have the data set X and Y, and depending upon what norm we choose, we get different type of fit. Now, one thing I want you to observe, and it is an interesting observation, that when the data is well aligned, so which means in the first figure, you will see all these data points are very closely aligned. You will notice E1, E2, or E infinity norm are close to each other. And this is actually very important. E1, E2, and E infinity norm, they are close to each other. However, as soon as you have an outlier, you would notice your E infinity norm goes out of bounds. So basically E infinity norm line, this equation shown by the solid line, solid thin line, is not the right answer. As a matter of fact, the solid dark line, which is E2 norm, is also not the correct answer, because as you can see, it is not fitting through most of the points. It's fitting through some of the points, but not all the points. But E1 norm, which is the mean absolute error type of norm, gives you the best possible equation for this approximation, wherein most of these points are fitted. So again, depending upon the norm that we choose, depending upon the equations that we used, that is very, very important. Now, we briefly talked about the gradient descent. What I want to do is, in the next part, I want to show you one more script that relates to the gradient descent. So gradient descent is, we are just trying to identify the direction where the derivative is becoming negative. And we want to find out the point where the derivative is 0. So what I'm going to do is I'm going to quickly go through gradient descent. And I'm going to run this code. So I will run this code. And this code, as you can see, is you have this equation, you have this function, you have x and you have y, and you will notice that there is this local valley and there is this global valley, and you are welcome to actually rotate it. And the way the gradient descent is going to work is it is going to find out the change, basically the gradient or the derivative along one axis, and is going to find out the derivative along the other axis. And then if this zigzag type of pattern continues, and please understand this is exactly the zigzag way the pattern is continuing. So for an example, if this is to get to this lowest point, we started here, went here, came down. And then here we noticed that it's going up. Then we started from here, went here, and came down. So the way the gradient descent works is gradually it goes in two perpendicular or two orthogonal directions, forward, left, and something, and that way. And then finally, what happens is it finds the local minima. But once again, it is extremely important where you start. For an example, if you start somewhere close to this global valley or global dip, you will definitely get to this point. But if you are going to start in the vicinity of this local dip, then you will get over here. So that is another important point that I would like you to keep in mind. And there are some variations of this. So for an example, you would observe that there is something called as the alternate descent. There are some optimal techniques for the gradient descent. There are different algorithms for gradient descent. But at the end of the day, the purpose is to find out the lowest point in the region. And gradient descent is the workhorse for deep learning and machine learning. So moving on to the next part is we have talked about the overdetermined system, underdetermined system, and then how do we solve overdetermined and underdetermined system. What E1 norm gives better fit compared to other norms. So to answer this question, please observe that when data is well defined or the spread is not too much or the data is well conditioned, then even E2 and E infinity norm, they behave the same way. So the answers are approximately one and the same. The problem comes is that when we have the data that is ill-conditioned, when we have the data that is ill-conditioned, we have some outliers, then the system or it won't behave properly. And the results that you are going to get, it's not going to be accurate. So even norm, basically when you are not sure like what type of fit I should use, your best bet is to start with even norm or perform some type of an optimization. Now let me answer this question again, and this is something quite interesting and important. Is if you have a system, so now what I'm trying to say here is let's see, let me define a model. So if I have an overdetermined system, overdetermined system. Now what does overdetermined system means? The number of equations. So number of equations greater than number of unknowns. So this system, if you want to visualize, this system will be shown something like this. So this is your A, this is your X, and this is going to be your B. And if you study classic regression, they talk about A as model terms. These are called as loadings. And these are called as outcomes. So in this case, model terms are known, outcomes are known, and we have to find out the loadings. Now here, there is another problem. Say for an example, typically we talk about this completely populated A. But please understand, when you are trying to solve an actual data science problem, this A may or may not be fully populated, which means there could be bunch of zeros. Sometimes the data for certain Bs may not be available. So basically, despite of these practical problems, you have to find out these loadings. You have to find out these loadings that satisfy somehow most of these equations given by Ax is equal to B. So how do we solve this type of problem? So to solve this type of problem, what we need to do is we will have to use an optimization routine. So we have to use optimization. And then again, you can define what type of optimization you want. So remember these equations that we talked about here. You can actually define which optimization condition that you want to use. What is the objective function? So if I were to say my objective function is minimize norm of Ax minus B, which is the L2 norm, plus some type of regularization. So now let me write this down. I want to solve this. So I want to solve this, but I cannot solve this randomly. I need to specify some type of objective function. And I need to specify some type of penalty or regularization parameter. And recognize objective function is what I really want to achieve. The problem here is this objective function can be achieved or may not be achieved. So I'm totally okay with this objective function not met fully. So I'm willing to penalize this objective function, which means I'm going to allow a little bit of error or a little bit of leeway. And I'm going to define this objective function as minimize. So ax minus b, and I'm going to use L2 norm, which is the square of the distances, least square, plus lambda multiplied by, I'm going to say norm of x. And believe you me that you can actually define however you want. So this is sort of the least square. And then this is nothing but the value of the E1 norm on x1. You can do it on E2, you can do it E infinity, whatever you want to do. So what I want to do is I have this problem and I want to find out the values of x. So basically find x where this objective function needs to be satisfied. So now what I'm going to do is I'm going to take you back to the MATLAB script and I'm going to show you that if I were to define this, how this works. So there's a question in the chat window. I think I answered that question. Let me share my MATLAB screen and I will show you what is happening. So now what I want to do is I want to actually solve this overdetermined system. And this code actually utilizes the CVX package that we installed in our last class. So let me quickly go through what is happening. So in line number 1, we are clearing everything. Then we are showing the underdetermined system. So values of n and m, these are the matrix dimensions. I'm creating a random A matrix and a random B matrix. And then I'm going to use this optimization package, which is CVX begin. I'm going to define the variable, and then I'm going to just find out the norm or L2 norm of this variable. And I'm going to define AX is equal to B. And please try to understand, this is nothing but the least square solution. So please pay attention. If I evaluate this, what's going to happen is I'm going to get a least square solution. Now, if I want to move to the next level, I want you to understand that instead of L2 norm, I'm creating L1 norm, which is nothing but the taxi cab norm or Manhattan norm. So I'm just minimizing the error and I'm defining. So if I were to do it something like this, and then I would get a different value. So I want you to look at, as you can see, it will actually give me all the number of iterations, objective, gap, and then finally it will give me the answer. So then what you can do, and actually you can run this code. And then again, it will do it. And as you can see, you have x2. This is the result of the least square solution. As you can see, these are the values of x2. If you type x1, you will get the solution. And I want you to carefully observe x2 and x1. So you will observe x2 is fully populated, but x1 is partially populated. So x2 has numbers everywhere because it's a least square solution. x1, which is the taxi cab norm or the sparse solution, has bunch of zeros. Now what I'm going to do is I'm gonna go further, and then you can actually plot the errors and then see how it works out. So for an example, what I'm gonna do now is I'm gonna plot these errors. So, and you will notice that I would generate this figure. And this kind of tells me the first solution, which is an L2 solution, and second solution, which is an L1 solution. Those are the weights. And then finally, you can actually look at the distribution. Now, this is for an underdetermined system. So we are currently solving an underdetermined system. Now, how would this approach work if we have an overdetermined system, which means number of equations are greater than number of unknowns? So what I'm going to do is I'm going to clear it all. And now I'm going to solve this overdetermined system. And for overdetermined system, please understand I have different values of lambdas. So evaluate. And then what I'm going to do is, and please understand that this is going to take some time. So this will take some time. So it will perform the optimization. And you will notice that you get this figure wherein you have the different values of lambdas, and depending upon the different values of penalty parameter or penalization, you get different solutions. And then if you were to go further, then you will notice that you are gonna get different values. So the last but not least is, this is a little complicated. If you were to have equation wherein your weights are not a vector. So I want you to understand, in the previous case, you notice that these are just single values. So basically I'm plotting the vector and the values. So these are the element 1, element 10, element 20, 21, 22, 23, 24, all the way to 100 elements. So now there are 100 elements, and these are the actual numerical values of those elements. If I were to perform the exact same type of analysis on a matrix, then it's significantly more complicated. And now it's going to take a lot more time. So please bear with me. And you will notice that it will need to perform the optimization for some time to get the loadings and the values. But one observation here, which I want you to notice, is optimization is the cornerstone of regression. And machine learning is dependent on sort of regression. So optimization is an important aspect of machine learning. So you would notice that depending upon the machine learning algorithm, different types of optimization, different types of approaches can be used. So here we'll wait for some time and let this calculation complete, finish, and then you will notice instead of a single line, you are going to have a rectangular matrix with different weights and different loading. Now, one thing I would comment here is regression is not a sort of X plus Y type of approach. Depending upon the problem that you are going to solve, depending upon your objective function, depending upon the amount of resources and time that you have, you use the appropriate regression algorithm. And here, there is a concept which is called as parsimony. So parsimony is something like the frugal. And so there is another interesting thing, which is something called as Occam's razor. So Occam's razor, which is something like a philosophical saying by William of Ockham, it goes something like that if you have multiple hypotheses that can be said for particular phenomenon, then most likely the simpler one is the most likely. So if you have multiple hypotheses, why is this thing happening? So the simplest explanation is most of the times the right explanation. And that actually leads to the concept of parsimony, where parsimony is used the model that is least complex that can be used to answer the data. So if you have data set, as an engineer, you want to find out the most simple explanation or the most simple model that will provide the answers. So it's something like keep it simple, KISS type of principle that is reflected in the laws of parsimony. So this is going to go for some time. And one thing I want to tell you that this parsimony approach is used in information theory as well. And you have something called as the information criteria, and that criteria is used for appropriate model selection. And once this calculation completes, I will switch directly on, and actually this will go on for some time, and at the end you will get a very nice plot, and that plot is going to be like when you solve the matrix equation. So now what I want to do is I want to kind of give you a little bit of information theory concepts, because information theory is quite important when we are trying to study the data analysis or trying to solve the linear algebra in the context of machine learning. So what I want to talk about is, so we got this model. How do we know this is the right model? So the way to find this is typically just like any neural network. You have a training data set and you have a validation data set. So you have this whole data set, and out of this whole data set, you would have partial data set that goes on to training, and then you have some partial data set you got for validation, and many a times you will have a small subset of data set. This is the test data set. So what you do is you do your training onto this, you perform your validation, see if you're getting good results on the data that is validated, and finally use this test to make sure that your approach and your algorithm, they are working. So one thing I want to talk about is there is information theory, and there are something called as the major theory. So, and if you're interested, there is information theory, and there is major theory. So they measure the difference or the distance between two probability distribution. So for an example, if you have two random variables, and then what we want to do is we want to find out the difference between these distributions, then you use something called as the measure theory. And this could be like a data set 1, and this could be the data set 2. So you can actually compare these two different data sets. And determination of appropriate model is the core. So they are used to find appropriate model. And if you are a hardcore information theorist, or if you are electrical engineering students, you probably take courses in information theory. And again, there are a lot of concepts which are like, if you have one model, so, or if you have one data set, you have other data set, how do you know if they are converging or diverging? So you have something called as the KL divergence. So KL divergence. And you have these different measures that are used to check the validity of model. Now, I want to give you not the information theoretic framework, but kind of more intuition. So if you have a model and if you have a measurement, so what we are trying to do is we will try to find out, compute, or we'll find out distance. And you can think about distance as an error as well. Error between the proposed model and actual data. So you try to find out the distance between the proposed model and actual data. And believe it or not, you have been exposed to something called as machine learning. Then you have something called as the Fisher's discriminant, or Fisher's maximum likelihood computation. Fisher's maximum likelihood computation. Then you also have something called as a Akaike information criteria, A1C, which is an A1C is not like the measure in use in diabetes or hemoglobin A1C. This is AIC. This is not A1C. This is called AIC. So AIC is Akaike information criterion. This is A1C. And then there is something called as BIC, which is something called as Bayesian information criteria. So you have AIC and BIC, and then you find something called as AIC scores. You have find something like BIC scores. And if you were to look at, and this is very important, if you are looking at system identification problem, and there is a lot of research that is going on system identification problem. So for an example, you have a bunch of this data set and you want to find out a model, and that could be some type of dynamical system. X dot is equal to AX plus BX square plus CX cubed, some model equation, or it could be in the form of some a sine omega tx, something like that. So how do you find out these equations? And please understand, these are derivatives. So these are the time evolution equations. So as time changes, these values change. So how do you compute all these based on the data? That is a very, very important system identification problem. And I want you to look at something called as Eureka, which is a numerical solver based on optimization and genetic algorithm to find out equation from data. Now, this is actually very important. So for an example, what people have done, and you will see the application of Eureka, what you have is, you have, say, cart and a pendulum. Okay, you have this cart and the pendulum. And honestly, the only data that is available to us is the displacement of the cart, velocity of the cart, angular displacement of pendulum, angular velocity of pendulum. And again, we have this time information. So you are going to take a video. So basically you have an actual physical system, which is a mass, a pendulum. Pendulum is oscillating and mass is going forward and backward. And what you do is you have this camera and you are going to take the video of this and feed that video to a machine learning model. So feed that video to a computer algorithm. And what this will do is, without knowing the actual value of mass, without knowing the actual properties, without knowing the length of the pendulum, it will give you an equation, which is something like mx double dot plus ml square theta dot, some other equation that describes the dynamics of this pendulum. And this has enormous implications. So a classic implication is, imagine that you have a robot. You have a robot and you want to model this robot, or you want to design this robot based on some biological phenomenon. Now, for an example, if you have birds flying, so if you have these birds or butterflies flying, okay, what you do is you actually take the video of this actual biological system. You take the video of this biological system, feed the video of this biological system to this algorithm, which will be some type of a genetic algorithm, machine learning model, or some type of a neural network model. And then what it will do is, based on this video, it will give you a model. And then that model will give you an insight, like how do I mimic this biological system in a robot. The other question is, imagine you have a human hand. So you actually trace, or you take the video of certain action that a human is performing certain action. And then what you do is you program your robot arm using the equations that are derived from observing this human motion. So developing data-driven models that are actually dynamic, that are real-time, that actually is a huge area of research. And that is actually the cornerstone of the next generation of robotics, machine learning, and data science. That is where we are going. So we are using neural networks. Now you have Chat GPT, you have generative AI, you have reinforcement learning, you have transfer learning. So they are all rooted into these fundamental concepts that come from data science and linear algebra. With that, we are done with chapter 4. The next chapter is going to be clustering and classification. And then we will gradually move on to the neural networks and deep learning. Then we will talk about the generative adversarial network, GAN networks. Then we'll move on to the dynamic mode decomposition and application of dynamics. Okay, so I'm gonna stop here and I'm gonna assign a homework for this. And if there are there any questions, I'm gonna stop recording.